Hello, and welcome back to the Mechanochemistry Discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. The goal of the seminar series is to bring our community together. The seminars stream live on the third Thursday of every month at 10 a.m. Central, 11 Eastern, and 4 p.m. GMT. They are also available to watch anytime on the YouTube channel. That YouTube channel is home to all of our previous speakers, and I encourage you to check out all of those seminars that are available. We also have an excellent slate of speakers lined up for the upcoming months. We hope that you will join us for them. A great big thanks, first of all, to Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students who helped with the seminar implementation, Quintarius Moore and Katie Floyd. Thank you so much for joining us. Please do follow, subscribe to our YouTube channel, and also keep track of us on Twitter. Before we get started, reminders that our webinar is being recorded. If you have any questions during the seminar, please email them to us at cmccdiscussions@gmail.com, or you can post them in the YouTube channel. Either way, they will be propagated to the speaker at the end of the presentation. Last but not least, it's my pleasure to welcome today's speaker. Dr. Bo Chen obtained his PhD in organic chemistry in 2011 at the Shanghai Institute of Organic Chemistry in China. He carried out postdoctoral research at the University of North Texas and Cornell University before joining Penn State University as an assistant research professor in 2018. In 2020, he started his independent research career at Donostia International Physics Center in Spain as an ICRBOSC Research Fellow. His research features creative application of computational chemistry to the research at the interface of organic chemistry, material science, and high-pressure science. His recent research focuses on high-pressure chemistry, nanothread chemistry and physics, as well as carbines and diradicals. It's my pleasure to welcome Dr. Bo Chen.
Thank you for the introduction, and thank you very much for the invitation. It's my great pleasure to be here to tell you a bit about the research in our group. So our research is related to mechanochemistry through pressure. So a major part of the research in our group concerns with the field of what I call computational high-pressure organic chemistry. Computational organic chemistry without high pressure is a well-developed field where people use calculations to study the structures, properties, and reactions of organic molecules. So why high pressure? What is interesting about high pressure organic chemistry? Here on the horizontal pressure scale, I'm showing you some of the areas that are related to organic chemistry that we are interested in. We have our normal one atom sphere chemistry here at about 10 to the 5th Pascal. In higher pressure in the fluid phase, we have chemical industrial processes such as Haber-Bosch process. Life emerges under extreme pressure at deep sea. So what's the chemistry there? What is the role of pressure in life? These are very interesting questions. In the solid state, we have diamond synthesis, nanothread synthesis, and even the claimed formation of a room temperature organic superconductor in the pressures of tens and hundreds of GPa. So a very important concept in understanding the effect of pressure on organic reactions is activation volume. So what is activation volume? The first thing we need to realize is that there is usually a volume change associated with a reaction. For example, here in this dimerization reaction, as the bonds form, the volume of the molecules becomes smaller because the relatively large van der Waals spacing between the molecules in the reactant state is replaced by the short covalent bonds. The volume reduction in this reaction is intuitive. Activation volume can be intuitively viewed as a volume difference between the reactant and the transition state. The volume we are talking about here is not simply the molecular volume. It is the volume of the whole reaction system. So if it's a reaction in the solution, then the solvent-solvent interaction, the solvent-solute interaction cannot be ignored when evaluating the volume. Activation volume is defined as the partial derivative of the free energy of activation with respect to pressure at constant temperature. There is a relationship between the free energy of activation and the rate constant K. So we can use the rate constant here in the equation so that activation volume can be both experimentally determined or theoretically calculated. To better understand activation volume, I think it's useful to make a comparison with activation energy. Activation energy, as we know, measures the effect of temperature on reaction rates, while activation volume measures the effect of pressure on reaction rates. To obtain activation energy, people use the famous Arrhenius plot, where the lowing of the rate constant K is plotted against 1 over temperature. Usually we'll get a line or a curve with negative slope, and with the negative sign here, we will obtain a positive activation energy. Similarly, for activation volume, we can plot lowing K against pressure. But what's different here is that activation volume can commonly be either less than 0, equal to 0, or larger than 0. I will give you some very intuitive examples here. So in 1967, William Noble compiled this very useful table of activation volumes of common reaction types. Bond formation reactions, where the molecules come together, has a negative activation volume, which is expected. Bond cleavage, the opposite process, has a positive activation volume. Bond deformation or isomerization, where the total number of bonds does not change, can have activation volume of 0. As you can see, activation volumes have been measured for other processes as well. But for this talk on pericyclic reactions, we'll be mainly looking at bond formation reactions, so negative activation volumes. Pericyclic reactions are especially interesting for high pressure studies because the cyclic nature of the transition state in these reactions usually lead to very large negative activation volumes. So the effective pressure on these reactions will be very big. Having introduced the activation volume, now I want to introduce the method we are going to use for activation volume calculations and high pressure calculations in general. And this method is called extreme pressure polarizable continuum model, or XP-PCM for short. This method was originally developed by Professor Roberto Cammi at University of Parma, Italy. And I joined the development about 2 years ago. Because this method is based on the traditional PCM method, so I will first review what PCM model is. The traditional PCM model or polarizable continuum model was originally developed to calculate the solvation energy of molecules or proteins. Okay. It uses the so-called implicit solvation, meaning that there's no explicit atomic structure of the solvent. Instead, the solvent is represented by this homogeneous dielectric continuum, which is characterized by a dielectric constant and an electron density. Then a cavity of appropriate shape and size is created inside this medium to host the molecule. Then we can evaluate the electrostatic interaction between the molecule and the medium. And this energy component is included in the total energy of the molecule. Of course, we can include other interactions as well. For example, cavitation energy, which is the energy that is needed in order to create this cavity inside this medium. Polyrepulsion, dispersion, hydrogen bonding are just other three interactions between the that we can have between the molecule and the medium. They can be useful in some other cases. It turns out that the cavitation and the polyrepulsion, they are going to be useful in XP-PCM, as we will see later. So here I want to emphasize the concept of the molecular cavity in the PCM model, because it's also going to be important in the XP-PCM model. The reason is that molecular cavity defines in a very natural way a volume for the cavity, or the volume for the molecule if you want. And this volume is going to be reduced when we apply pressure to the molecule. So the basic molecular cavity is the van der Waals cavity. It can be constructed by overlapping atomic spheres with corresponding van der Waals radii. And we also introduce a scaling factor to control the size of the radii, the sphere, and also the volume of the cavity. And of course, more complex cavities, such as a solvent-excluded cavity, can also be constructed based on this simple van der Waals cavity. Now I want to talk about the extension of PCM to XP-PCM. But before that, I think it would be helpful to review what is pressure and what is the effect of pressure on the molecule, so that we know what to expect from the XP-PCM model. Pressure, as we know, is simply force over area. And this is actually can be called the mechanical definition of pressure. There is, however, a thermodynamic definition of pressure, which says that the pressure is the negative of the partial derivative of internal energy of the system with respect to the volume of the system. Of course, this is a macroscopic definition of pressure because it uses an ensemble of molecules. So now if I ask the question, how can we adapt the definition of pressure for just one molecule? Okay, so the reason we are interested in one molecule, because that's what we want to do calculations on. From a computational point of view, one molecule is much easier to work with than an ensemble of molecules, right? Of course, you can do molecular dynamic simulations on many molecules, and there the pressure can be well defined if you have a unit cell. But here in the XP-PCM, we actually use something very similar to the second definition of pressure. So for a single molecule, the internal energy, especially at 0K, can be approximated by the electronic energy of the molecule. And the volume for a single molecule is just the cavity volume from the PCM model. So both quantities are easy to obtain. Then what is the effect of pressure, and what features the XP-PCM model should have in order to model the effect of pressure? Right, so the first thing we need to understand is that pressure is applied to the molecule by its neighboring molecules through intermolecular repulsive interactions. And in a fancier language, we can say that at microscopic level, it is a penetration into the repulsive region of intermolecular potentials. And because of this repulsive interaction, the molecule under pressure will experience an increase in its electronic energy and a decrease of its volume. So two things here, energy increase and volume decrease. They are the two effects of pressure, or two consequences of applying pressure to a single molecule. And they are actually exactly the two quantities that we need in order to implement the pressure in XP-PCM using this definition. So now what we should do is very clear. in the XP-PCM, we should reduce the volume, and we do that by scaling down the van der Waals radii of the spheres. We should also introduce an intermolecular repulsion, and we do that by introducing the polyrepulsion between the molecule and the medium. Specifically, we introduce a step barrier at the boundary of the cavity, and any electron density of the molecule that is outside of this cavity is going to experience this polyrepulsion with the medium. And as we decrease the volume of the cavity, there's going to be more electron density lying outside of the cavity, so that the repulsion is going to be stronger. Then the energy of the molecule will be higher and the pressure will be higher. So now that we have understood the essential ideas of XP-PCM, what's left is just a few technical points and some symbols that I want to introduce in order to better prepare us to understand the applications of this method. So in the XP-PCM pressure calculation, we use the electronic energy, GER. The E here stands for the electrostatic interaction, and that's introduced in the original PCM model. R stands for the repulsive interaction that we introduced in the XP-PCM model. VC is the cavity volume. So in order to study reactions with volume changes, we need to add on top of the electronic energy an additional term, G, called cavitation energy, GCav. This term includes the PV volume work and an entropic term related to the density of the solvent. And we just call it G non-PV, just to distinguish it from the PV work. So now let's move to the applications. I'm going to show you the calculations on 4 pericyclic reactions. And for each one of them, I will highlight one interesting finding or interesting prediction or interesting highlight, or interesting insight from the calculations. So let's begin with the Diels-Alder reactions. This is the Diels-Alder cycloaddition between cyclopentadiene and ethylene, forming 2 bonds that are labeled in red. So organic chemists like to use this kind of drawing, where by default, these atoms are carbon atoms, and the hydrogen atoms are usually omitted. But the hydrogen atoms are going to be there, as we see in the structures below. And there's actually as many hydrogens as necessary on each carbon to complete the valence octet of that carbon atom, okay? So in the calculations, we start with a optimization of the transition state in the gas phase for the reaction. And once we get that, we follow the so-called minimum energy path to map out this potential energy surface for the reaction. And each point here on this curve represents one structure along the reaction coordinate, so that we can follow the geometric evolution of this reaction from the reactant to through the transition state to the product. The reaction coordinate here with this weird unit, square root of atomic mass unit times Bohr, is a mass-weighted one-dimensional coordinate that essentially gives us a one-dimensional representation of the reaction, which is very convenient. The calculations are done with density functional theory, either for the gas phase calculations or high pressure calculations. And back to the reaction. This reaction has a barrier of about 21 kcal per mole, and it's exothermic by 23 kcal per mole. So for the high pressure calculations, we start with the gas phase structures, which is shown here again. And for each one of them, we do an XP-PCM calculation. Okay, so no geometry optimization here, just single point. So if you have questions about the geometry optimization, just ask question. I'll explain it later. What an XP-PCM calculation gives us are the energies of that structure at different pressures. And the energy I'm talking about here is the total energy, which contains electronic energy and the cavitation energy. From that calculation, from this data, XP-PCM data, we were able to construct the energy profiles for the reaction at different pressures, as I shown here. Okay, so one of the first observation we have here is that we can see the barrier of the reaction decreases as we go to higher pressure, and that is expected because this reaction is a bond formation reaction. It should have a negative activation volume and should be favored under pressure. We were also able to calculate the volume profile of this reaction, which is shown here. We see a relatively flat region at the beginning of this reaction. That flat region corresponds to when the two molecules are basically trying to find the correct orientation for the bond formation, and that they are approaching each other slowly. And during the bond formation, the volume decreases substantially. That makes sense. So everything here in the volume profile is reasonable. We observed a very interesting correlation between the volume and energy profiles. Let me explain. So whenever we have a flat region in the volume profile, the energy curves in the energy profile are going to be more or less parallel. The reason is that the effect of pressure is small because the volume change is small. Okay. However, whenever we have a volume decreasing region in the volume profile, the gaps between the energy curves are going to increase. So the gaps are going to increase. So why is that? Let me just randomly pick 2 points on the volume profile, A and B. B has a smaller volume than A, right? So the structure at point B, because of its smaller volume, it should be stabilized more under pressure than A does relative to the reactant, right? If you look at the energy profile, let's just focus on the 0 GPa curve and the 11 GPa curve. B does have a larger stabilization, right? And that is due to that B has a smaller volume. So a volume decreasing region, the gaps between the energy curves increase. Okay, so let me summarize again the 2 observations here. And actually, I'm going to call the 2 observations 2 rules. Rule number 1, if we have a flat volume region, the energy curves are going to be parallel. Rule number 2, if I have a volume decreasing region, the gaps between the energy curves increase. Okay, so especially rule number 2 is going to be very important because we are going to use it multiple times in the later discussions. The second reaction is the 6+4 in reaction. 6 and 4 here just count how many electrons are involved in the transition state. So in this reaction, the CC double bond, the 2 CC double bond, and 1 CH bond from the bottom ring are the 6 electron component. The die-in from the top ring is the 4 electron component. So this is a 10 electron cyclic transition state. In the reaction, a CC bond is going to form here on the right, and this hydrogen is going to be transferred to the top ring. And this would be our product structure. We have here the energy profile at different pressures and the volume profile below. So we see similar things here. That is, the barrier decreases as we go to higher pressure. And again, that's due to the bond formation nature of this reaction. What's new here is that there is a clear shift of the reactant minimum towards the transition state. And to explain this shift, we can use the rule number 2 that we just summarized a few slides back. And rule number 2 says that whenever we have a volume decreasing region, the gaps between the curves is going to become bigger. And that is exactly what happens here. The gaps are definitely larger here than they are here, right? We also see that the transition state actually shifts towards the reactant. The transition state was originally here at 0 GPa, but it shifted to here at 6 GPa. So what's interesting is that we can also use the rule number 2 to explain this shift. Notice that in the transition state region, the volume is still decreasing. Then according to rule number 2, the gaps between the energy curves is going to increase, and that is right. So here we have something very interesting. We just use rule number 2 to explain the shift of reactant and the shift of transition state, but towards different directions, opposite directions, right? Think about that. So the underlying reason for the shift is the same. That's because the volume is decreasing. But the behavior or the directions of the shift are totally opposite. And why is that? Turns out that the reason is, the curvature of the energy curve matters. So near the minimum, the reactant minimum, the curvature is positive. Near the transition state, the curvature is actually negative. So that it is a different size of the curvature at different points that leads to the opposite directions of the shift. We actually discussed this effect in detail in this recent theory paper. We also noticed that the opposite shift of the reactant transition state actually brings them closer to each other, right? That just means the transition state becomes earlier in the high pressure reaction. And that is actually consistent with Hammond postulate. The Hammond postulate says that the more exothermic the reaction, the earlier the transition state. This reaction does become more exothermic when we go to high pressure, so that the transition state also does become an earlier transition state at high pressure. Now let's move to the electrocyclization of hexatriene, this molecule. The most stable conformation of this molecule is the extended form, and it does not have the correct geometry for bond formation at the terminal carbons. What it needs to do is to undergo the conformational changes to this folded conformation, if you want, before the bond formation can occur. The bond formation, usually at 1 atmosphere, it has a much higher barrier than the conformational changes. And it's usually the rate determining step of the reaction. So let's see if that's going to change under pressure. This is a volume profile for this reaction. We can see that the 3 conformations have quite similar volumes. All of them are larger than the product. But what's actually most important here is that the transition state 1 for the conformational change has a larger volume than the reactant. Transition state 3 for the bond formation has a smaller volume than the reactant. So we would expect that transition state 1 is going to be destabilized under pressure. and transition state 3 should be stabilized under pressure. So in the calculated energy profile, going from the 0 GPa to 14 GPa, we do see that TS1 gets destabilized, the energy increases, and TS3 gets stabilized, the relative energy decreases. And at 14 GPa, TS1 actually has a higher energy than TS3. That means the rate determining step for the reaction is no longer the bond formation reaction, but a conformational change. And this is a very interesting prediction. And it has not been verified yet. But I think that people have measured the activation volumes for other conformational changes. So conformational change can become important under high pressure. Okay, the last reaction. We are looking at here the Sigmatropic rearrangement or the Cope rearrangement. This reaction is a symmetric reaction in the sense that the reactant and product are the same. In the transition state, the two bonds, one to be broken and the other to be formed, are of the same distances. Here we ignore the possible conformations from the rotation about these single bonds, and we just focus on the bond formation, bond breaking step. So you know what we are going to do, right? We are going to look at the volume profiles first, analyze it, make predictions about the energy profile, and then verify that from the energy profile. So the volume profile tells us that the transition state has the smallest volume, and that's reasonable because the transition state is a cyclic structure, but the reactant is a linear molecule. So we would expect that under pressure, the transition state is going to be stabilized. And that's exactly what happens here. Transition state goes down. But even at the highest pressure we have in the calculation, there is still a sizable barrier here. We see the shift of the reactant towards the transition state. That's expected. The transition state does not shift to the left or right because this is a symmetric reaction. The question we were wondering is, can we turn this transition state into a minimum if we go to sufficiently high pressure? It seems possible because under high enough pressure, the PV term, which is included in the cavitation energy, is going to dominate the electronic energy so that the transition state can become a minimum. But we haven't done the calculations yet. We don't know how high the pressure would be needed to make that happen. And we also don't know whether that pressure is a realistic pressure. So this is still an open question at this moment. As you have seen in the previous examples, I have used the volume profile extensively to analyze and understand the energy profiles. So the first take-home message is the cavity volume profile of a reaction proves to be a very useful diagnostic for analyzing the effect of pressure on the reaction. So in the next few minutes or so, I'm going to talk about the dimerization of 1,3-cyclohexadiene, focusing on using activation volumes to distinguish reaction mechanisms, and also on analyzing the origin of activation volume. So here we go. In 1986, Knoller reported that the dimerization of 1,3-cyclohexadiene forms these 5 products. The first 2 are from the 4+2 cycloadditions. The next 2 are from the 2+2 cycloadditions. The last one from the in reaction, which we actually have looked at before. This is, of course, a complex reaction, 5 products. And we have in organic chemistry a very famous rule called Woodward-Hoffman rule, which says that the 4+2 cycle addition under thermal conditions is symmetry allowed reaction, but 2+2 cycle additions are symmetry forbidden reactions. So the implication of that is the 4+2 products and the 2+2 products cannot be formed from the same mechanism. Okay, so the message here is there must be some multiple competing mechanisms at work in this reaction. Okay, the 2 major competing mechanisms in this reaction is the so-called concerted and the stepwise mechanism. I'm going to use the endo product to explain these the differences between the 2 mechanisms. So in the concerted mechanism, the 2 bonds are formed at once in one step simultaneously. But in the stepwise mechanism, 1 bond is formed initially, generating this intermediate with 2 radicals or dangling bonds if you want. Then in the second step, a rotation about the single bond and a bond formation can lead to the same endo-2 product. These are the same product, although they are drawn differently. They are actually mirror images here. So the major difference between a concerted mechanism and the stepwise mechanism in terms of the volume is that the concerted transition state, because there are 2 bonds connecting them, should be a more compact transition state. So its volume should be smaller. If its volume is smaller, then the change of volume from the reactant to the transition state should be larger in the concerted mechanism. And that just means the activation volume from the concerted mechanism should be more negative or larger than from the stepwise mechanism. In the experiment, they have measured the activation volume for the formation of all of these 5 products. They do get 2 relatively large activation volumes and 3 relatively small activation volumes. In our calculation, we can calculate the activations for both the concerted and the stepwise mechanism, right? What we got is an excellent agreement if we use a concerted mechanism with the formation of endo-2 and the formation of 304. From the stepwise mechanism, we get a relatively good agreement with the formation for these 3 products. So from these calculations and the comparison with the experiment, we can say confidently that the first product and the 5th product are formed by a concerted mechanism, but the rest 3 products are formed by a stepwise mechanism. So we were not only able to compute accurately the activation volume, but we can understand why they are different. Shown here, the computed activation volume of the stepwise transition state, the 4+2 transition state, and the 6+4 transition state. And as we can see in the transition state structures here, as we go from the left to the right, the facial overlap between the 2 rings increases, so that the transition state becomes more compact, and that leads to a smaller volume for the transition state on the right. And that is the reason for the large activation volume for the transition state on the right. We can go one step deeper to decompose the activation volumes in order to get to the origin of activation volume. So if you remember, our total energy for the system has the electronic components, has the PV volume work, has an entropy term. Then because the activation volume is calculated from the total energy, then activation volume will also have an electronic contribution, an entropic contribution, and a change of molecular volume, right? So, or cavity volume. So let's take this reaction as an example. Out of the minus 28 cubic centimeter per mole activation volume, about half of it comes from the molecular volume change, but we do have substantial contributions from the entropic and electronic terms. So if you remember at the very beginning when I introduced activation volume, I said that the volume is not simply geometric volume. If it's a volume of the reaction system. If it's a solution reaction, then the solvent-solvent interaction, the solvent-solute interaction should be considered. The electronic contribution here because it contains the electrostatic interaction and the poly repulsion somehow reflects the molecule solvent interaction. The entropic term is related to the solvent density, so it somehow reflects the solvent-solvent interaction. So the molecular, if you use the molecular volume change to as the activation volume, it would be a huge underestimation, but it is indeed a major contribution. So that if for a qualitative discussion, the using molecular volume would be okay. So that's actually what we have been doing in the discussion when we use the volume profile to understand the energy profile. And with that, I will have two take-home messages. And with that, I will thank you for your attention, and I'm happy to answer any questions.
Thank you very much for that presentation. We have a few questions from the audience. For the non-expert, how does one apply pressure in DFT? Okay, so yes, so that goes back to the method. So in DFT, in our model, let me go to the slide. So this is how we get the pressure from the electronic energy. So in DFT, the electronic energy can be computed at any level of theory, at DFT or at wave function level or empirical level, whatever you have. The important thing is that we need to have this poly repulsion component in the model. Once we have this poly repulsion, we can introduce pressure. Okay. All right. Thank you. Excuse me. Thank you very much. In an earlier slide, you had a table with activation volumes that showed that bond deformation corresponded to a zero activation volume. If a bond gets shorter, doesn't that mean that volume changes? Yes, but here you have to consider not just one bond. You have to consider the whole molecule, right? And also the interaction between the molecule with the environment. So it's not easy to say. You see, they say it's almost to zero. It's not exactly zero, right? So, and all these numbers are actually average numbers over many, many reactions. So it's not one bond corresponding to 10, it's an average number. All right, thank you. Next question, would you mind explaining why rule number 2 is able to connect the change in volume to energy? Okay, yeah. So rule number 2 says that if the volume decreases, the energy gap increases, right? The point A has a larger volume than point B. So if we apply pressure to the two structures, the structure with a smaller volume should be stabilized more, right? Because the PV term, if V is smaller than PV is smaller, then PV is added to the total energy, then the energy will be lower. So B will have a lower energy, lower total energy.
at higher pressure than A. Lower energy means it is stabilized more, right, relative to the reactant. And here on the energy profile, the stabilization is shown by this red line. So that's the stabilization we got from changing pressure to 0 to 11 GPa. Yeah, I hope that helps.
All right, thank you. Here's another one. The pressure calculated from the cavity volume is a normal or hydrostatic pressure. Is it possible to simulate the effect of shear stress? And if so, how?
Yes, the pressure calculated from this model is a hydrostatic pressure because the polyrepulsion we applied to the cavity that is homogeneous or isotropic. The polyrepulsion is the same everywhere. The polyrepulsion, the potential is the same everywhere on the boundary. So for shear pressure, then you have to somehow introduce the polyrepulsion potential that is able to be, to be different at different sides of the molecule, or, has to be different. And that's going to complicate the theory, the model, and also the implementation. I don't have a good idea of how to do that with this model.
All right, great. Let's do just one more question. Near the end, you mentioned that one could use activation volume change qualitatively to compare different cases. Under what conditions can you ignore the other two contributions and just use the volume change?
Yeah, so in what case can I ignore these two contributions? So this activation volume decomposition, we have only used it, I have only done it for this one reaction. We don't know how it looks like for other reactions, whether these two contributions will be much smaller or much larger. So if you want to ask one example, I really don't have a good example. Maybe, so what I can say is that the electronic contribution comes from the two structures. If volume is different, the one with a larger volume, their electron distribution, electron density is more diffuse, and it's going to feel the pressure first, and the energy is going to increase faster. So if we want to kill this electronic contribution, then somehow the electron density distribution should be similar in the two structures, the transition state and the reactant. And I don't have a good example for that right now. So the entropic term is more, less intuitive. It's related to some number density of the solvent, and the solvent is actually a median. So it's less straightforward to say how can we kill this entropic contribution. I hope that answer helps.
All right. Well, thank you for those questions, and thank you so much for the seminar.
Thank you.
Thank you, Dr. Chen, for that outstanding presentation. And thank you all so much for joining us. Again, if you've missed any of the seminars as part of mechanochemistry discussions, they are all available to watch anytime on the YouTube channel. We also have a great group of speakers lined up for the upcoming months, and we hope that you'll join us for all of them. Thank you again.